All right. So, the first thing we need to learn in order to understand how all of this works is we've got to learn how to count like a computer counts. Because computers are just fast math machines. Okay, that's all they are. They're just really fast calculators. And but they do math in a really odd way. And you need to understand how they do math in order to really be able to hang on. Let me see if I can get my thing paired here. Remotes. Unlink. Add a device. Link. Confirm. Okay, let's see if that works now. It's hunting for it. All right, well, I'm going to let that think for a minute. Okay, so we need to learn how to count. To learn how to count, like a computer, we first need to relearn how to count like a human. Because you've all forgotten how to do that. Okay? You learned this a long time ago, and now it's become second nature to you that you forgot how it works. Okay? And you're all going, what are you talking about, Jason? I count every day. I know exactly what you give me a minute, and I will explain. I'm going to start by asking you a question. How much is a dozen? Okay. Great. What's that? It depends, yes. It does.
Am I a baker or not?
Yeah, that's right. That's right. So, yes, of course, you would say it was 12. Okay, well, how much is 12? 12 is 12, right?
That's why they call it 12.
Okay, so hang on a minute. Let's go back to, like, first grade. How would you have explained this in first grade if your teacher asked you how much is 12?
Well, you know, back in first grade, you'd have to divide the units up into like hundreds, tens,
Yes.
ones.
So when you were in first grade, your teacher would have said 12 is one set of tens and two ones. Do you remember that? Is it coming back a little bit now? Let me explain. Decimal is the numbering system that we use to count, okay, that humans use to count. Okay, and it uses 10 digits. These are the digits, okay? Those are the characters that we use to represent all the different values in the decimal numbering system. So you can start at 0 and go all the way to 9. Well, what do you do when you need to do a value more than 9? Yeah, you reset to 0 and you pick up a new little, we call them decimal places. You shift one place and you start over again. So, and each decimal place is 10 times greater than the one before it. So, for example, if we look at just the digit 1 all by itself, it is currently representing a value of 1 because it is sitting in the ones slot. Okay? But what if I move it? Now it represents 10. Why? Because that 1 is now sitting in the tens slot. So I have 1 10 and no ones. Is this coming back to you now? Starting to remember how this works? What if I move it again? So now I got one set of hundreds, no tens, and no ones, which is 100. I have one set of hundreds. Have I lost anyone yet?
Yeah, well, I mean, it's not exact. I can't remember exactly doing that from first grade, but I do remember like regrouping.
Yeah, yeah. Believe it or not, this is how you learn to count. in elementary school. It was a long time ago, and you've forgotten it, but this is how you learn to do it.
I have no memory of them teaching me to count.
Yes. Okay. What about this? The digit 1, 2, 3. Well, you've got one set of hundreds, two sets of tens, and three ones, which is 123. Now, you've gotten so used to doing this that you just look at that and go, oh, it's 123. And a long time ago, you stopped thinking how many hundreds, how many tens, and how many ones. But originally, that's what you used to do. When you were a kid, you used to look at that number and you would say, okay, I've got 1 hundreds, I got 2 tens, and I got 3 ones. And you'd put that together, and that would be 123. Okay? That's how you started doing this. And you just got so good at it that you realized that you didn't have to do that anymore. You got really good at looking at these numbers, and that little shorthand is like happening subconsciously in your brain, and you don't have to think about it anymore. But it is happening. You are looking at that, and you are doing that. Okay? You've just gotten so fast at it that you don't have to think about it that way anymore. But understanding these different numbering systems that I'm about to throw at you requires that you think about it like this again. Okay? So before I move on, I will ask again, have I lost anyone? Everyone feeling good about this? Okay. Is this going to give me the remote yet? No. I'll have to figure that out later. Okay. There's another really important point here that will become even more important when we start looking at the different numbering systems, is that 0 does not have a value. Okay? When you put a 0 in one of those slots, it just represents that there is no value for that slot. And all of the possible decimal places, all of the possible slots that could be used to describe a value, like in this case I've got thousands, 10,000s, 100,000s, those exist. In every number, they exist. We just choose not to show the ones that have no value, that are higher than whatever the highest one is that has a value. We usually hide those. We call them the leading zeros. We usually hide them, okay? But they're there. They're always there. We just choose not to look at them. But knowing that they are always there is really important, especially when it comes to thinking about how computers look at numbers, okay? Because the computer does look at them. The computer doesn't hide them. It knows that those leading zeros are there, and it has to count them in order to do anything, which is why, for example, storing a value of 1 takes the same amount of space on your hard drive as storing a value of 256. It takes the same amount of space on your computer to store both numbers. Okay? Because the computer has to store those empty slots anyway, even if you're not using them.
Well, doesn't that mean it has infinite empty slots?
No, because there is a limit to the architecture of the computer. So you've heard about like 32-bit CPUs, 64-bit CPUs, stuff like that. That is all about how many slots is it able to look at one time. And that dictates sort of how it has to divide up the number chunks. Okay? That will become more important later. All right? But this is a very important concept that you need to understand, that these empty values exist, whether you see them or not. They are there. Okay? But usually when human beings look at numbers, we choose to hide those. But computers don't hide them. Okay? They can't hide them. All right? So now let's learn a different numbering system. Okay? Turns out there's lots of ways to count. And decimal is not the only way. It's not even necessarily the best way or the most efficient way. It's just the way that we learned. Okay? So let's learn a different way called hexadecimal. Well, let's break down that word. Hex stands for 6, and des stands for 10. So if decimal is a base 10 system, then hexadecimal is a base 16 system. Okay? So hexadecimal uses 16 digits, whereas decimal uses only 10. And these are the 16 digits that hexadecimal uses to represent all the various values. And let's count to 10 in hexadecimal. Are you ready? So this will be making sense at first. 2, all right, 3, 4. Okay, everybody following along? 5, 6, 7, 8, 9, 10. 10. That's not A.
10.
In hexadecimal, that is not an A.
None of them look like a 10.
In hexadecimal, that's a 10. Okay? Did I lose anybody? You with me so far? Okay. Let's try 15. We'll start at 9. 9, 10, 11, 12, 13, 14, 15. So in hexadecimal, that's not an F. That is a 15. Okay? Did I lose anybody there? You with me so far? Okay. Let's break this down a little further. So what if you want to do 16? Well, just like how in decimal, which is a base 10 system, every little slot or decimal place is 10 times higher. In hexadecimal, every slot is 16 times greater than the one before it. So we got to 15 and we ran out of digits, right? And because this is the digits you use in hexadecimal. We got to 16 and we didn't have any more. So you want to go to 16, what do? Well, you reset the ones back to the beginning and you put a 1 in the next highest value, which is a value of 16. So the digits 1, 0 represent 16 in hexadecimal. Eric, you have a question?
Just hit me. I know this is not like the equivalent to an imaginary number, but like, could you consider this like an imaginary?
No, it's not imaginary. We're just representing it in a different way. 16 is a real number.
Well, yeah, but 16's like units separate. That's sort of like what's throwing me off a little bit. Like, if you consider it a like.
We're just using a different numbering system.
Okay.
We're just counting it in a different way. Okay? It is just as real. Okay? This value of 16 is just as real in hexadecimal as it is in decimal. It's just we're representing it in a different way. Okay? So one set of 16s and no 1s. Okay? So let's compare now decimal to hexadecimal. So here's the digits 2, 0. Well, you're used to looking at that and going, oh, that's 20, right? And you forgot that you're supposed to go, oh, it's two sets of 10s and no 1s, right? You just go, it's 20. But what it really is 2 sets of 10s and no 1s. Well, now you've got to ask yourself, well, what numbering system is that? You assume it's decimal because that's been the default your whole life, but in this class, it's not necessarily going to be the default. Okay? I might throw numbers at you in a different numbering system, and you need to. So this is where the "it depends" answer comes in. Like I throw a number at you, and I say, "What is that?" You say, "It depends." You're right. Yeah, it depends on what numbering system we're using right now. Okay? And if we're using hexadecimal, that is 32. Right? And why is it 32? Because it's 2 sets of 16, right? And no 1s. That's 32. Okay? You with me so far? If I lose you, stop me. We got plenty of time to cover this. This is the only thing I want to talk about today. So,
If you're on your way there, you can stop. But what would a number that involved a letter look like? Like if we were to have.
oh, yeah, I'll show you.
Yeah, I was like, you might be on your way there.
So here's a chart of values of 1 from ranging from 1 to 30, represented in both decimal and hexadecimal. Okay, so 1 through 9 look exactly the same, and then you start heading along your way, and we get to like 26, for example, in decimal. That's the numerals 2 and 6, and in hexadecimal it's 1A. Well, you know that A represents 10 in hexadecimal, so it's one set of 16s and 10 ones, which is 26. See how that works? All right, stare at that for a minute and try to see if you can understand all these different values and why they mean what they mean. And if you see one you don't understand, let's talk about it. Yeah.
Suddenly it's a 216.
Yeah.
15 ones.
Yeah. So this one is one set of 16s and 14 ones. Right? That's 30. Okay. So maybe you're thinking, Jason, why is this important? Because this seems really stupid, like a really dumb way to count. Why is this important? Well, anybody thinking that? Anybody willing to admit you're thinking that? Like, come on, Jason. Like,
Stupid. Just like, why?
why?
Yeah, less stupid and more like, I don't know the application. I don't know when.
Okay. So I will give you a little like teaser as to why this is important. Computers don't count in hexadecimal. Okay, computers count in binary, and we're going to talk about binary next. But computers count in binary in chunks of 8 digits. And chunks of 8 digits abstract really well into hexadecimal. And so hexadecimal is a much easier way for us to look at binary numbers. And in fact, when you program in MIDI, if you read the the general MIDI specification, most of it is written in hexadecimal to represent the binary digits that are happening under the hood. Okay, and so and because of that, because we're trying to use hexadecimal to represent the binary values, the hexadecimal imposes certain limitations onto those different control protocols that are very important because of the limitations of the way these little groups of 16s work. Okay, you'll start to see how that works. But we use hexadecimal as a way of abstracting binary, because we can look at the hexadecimal values and really quickly convert that into what the binary equivalent is, and then understand what must be happening in the computer as a result. You can go from hexadecimal to binary in your head much quicker than you can go from decimal to binary in your head. Okay? And that's why it's useful. And vice versa. You can go from binary to hex in your head way faster than you can go from binary to decimal. Okay? You ready for binary now? Okay. Well, hopefully you know that the bi in binary means 2. Okay? So binary is a base 2 numbering system. So we only get 2 digits in binary. It's 0 and 1. Now, why? Why would you do that? That sounds like really inefficient. Well, remember that computers are just really fast counting machines. And machines tend to, well, computers in particular, involve a lot of switches. Okay, like a CPU is just a bunch of transistors. Okay, and the transistors can go back and forth, back and forth. They can either be this or they can be that. They can be this or they can be that. They can be on or they can be off. Okay, that's all they can do. They can just be on or off. There's nowhere in between. It's either on or off, yes or no, right or wrong, 1 or 0. That's all. That's all it can do. And so that's the mechanical limitation of computer technology. There's just a real mechanical limitation of how that works. Now, as an interesting little sidebar, one of the things that is really interesting and really exciting is, like, could we design a computer that could have more than just 2 states, on and off? Turns out, yeah. We're working really hard on that right now, actually. We humans, on planet Earth, we're working on that. There's a couple of ways to do it. One is using quantum states. So, so it turns out you can, if you pay attention to the quantum states of particles, there's more than just 2 values. So that's a possibility. You could have a quantum computer. There's also kind of biological computers, which is like DNA-based computers. So you can use like organic material and use the DNA in organic material to store lots of different possibilities of numbers, right? And which some would argue is basically what we are. But you can make a machine that would do that. There's a really interesting book, I believe it's written by Robert Ludlum, called The Paris Option. And if you're interested in a fun little, just read, The Paris Option. Robert Ludlum wrote like The Bourne Identity and stuff like that, spy books. Okay, well, he wrote this like espionage book about a researcher that actually got a DNA computer to work. I mean, they work. I mean, there's one. They have them at Duke University. Okay, like these things exist, but the trick is getting software to run on them. It's just like it's a whole different way of like machine coding. And so the book.
This is terrible.
So the book was about, hey, what the real innovation was, there was the computer scientist somewhere that actually got some software to run on this thing, and suddenly, of course, it becomes sentient and takes over the world. Okay, because like its ability to crunch numbers is like as good at it as we are, but controllable, right? And it's just mind blowing, the capacity of these things. So there's a lot of work and research going into this right now of trying to figure out how to build non-binary computers that can count in ways that aren't limited by 0 and 1 or on and off. And that opens up enormous possibilities.
Like what? Like what does that give us, like, the option to do?
Well, for example, encryption would get a lot better, because if each little particle in the computer can have more than just a binary state, then suddenly you can encode massive numbers without anywhere near as many components.
Who needs to encode those massive numbers, though?
People who are trying to encrypt data that cannot be hacked.
That's what, this just sounds like a government employee.
But also, imagine a computer that wasn't constrained by 64 bits.
Okay.
Maybe that supercomputer from
So would it
Dead
jump to
Reckoning.
128? Would that be the next?
No, it would be like
Unlimited.
unfathomably bigger than that.
Okay, cool.
I mean, it could do insanely big and complicated math instantly.
So, like, rocket scientists, they could finally, like, maybe produce that, like, it would take the people out of that?
Maybe.
Maybe? That's kind of cool.
I mean,
Kinda. Because then it leaves spots for people to expand more.
we're sort of not there yet, but we're just in theory the capacity of the computer, its capacity to do big, hard, complex things quickly would grow exponentially, and so suddenly it'd be like literally a quantum leap, in computing power. Yes. That's it's a TV show. Okay. So anyway, that's a little sidebar. But at the moment, most of our computers all the computers you're probably interacting with are still constrained by this concept of the transistor, which is binary. But I do think it's probably within our lifetimes we will start seeing, actual functional quantum computers or, biological computers that would like blow our minds on what they can do. Yes.
Well, wouldn't that be like basically promoting artificial intelligence?
Well, yeah. So that's the promise of it is that's the other thing is artificial intelligence becomes a lot more achievable when you're not limited by binary. Okay. So.
Did you see Mission Impossible: Dead Reckoning?
Oh yeah, yeah,
I mean, that computer that they're after, like the future.
yeah.
What do such computers look like? Like, physically?
I don't know. I've never seen one.
I just looked it up. Like, they might have a beating heart.
Being out, we're imagining, like, the stem and some dirt
leaves.
and then butter. Like, that's what I
I don't know. Well, now you have something you can Google tonight. Okay.
I guess so.
But we're still constrained to binary, so that's what I'm going to teach you is binary. So we're going to skip to the end here, and let's see if you can make sense out of this. This is the decimal and binary comparison. So stare at that for a minute and see if you can figure it out.
I actually.
I lost it at 4. I got lost at 2. Talk in your head, please. No.
Is 20? Oh. So
Oh,
number
oh,
20.
oh, wait, no.
So would 20 be 20 is 10 and 100? Would that be 2 sets of 100?
Same, that's what I want.
It's binary. There's no concept.
I think
Yes.
I understand it. Is 32 100,000?
No.
What?
No, 32 is 32, but in that
Oh,
representation,
So
what has to be.
You're thinking about it the wrong way. It's not.
But I don't know what the thing is. What if it's. Oh, Jason!
No, it should make
Is
sense.
can I explain this
Yeah,
out loud? Is it
yeah.
okay? So, 0, 0, 1, 1. The 0 is a 1s, but the second place is a 2.
Yeah.
Yeah. And then at 4, it goes to 4 on the end. So it's 0, 2, 4, 6.
Well, no, it doesn't. There's no
Well,
sixes.
Oh, it goes to 8.
Yeah.
And then 16. And then
Yeah.
32. Okay.
Yes. Okay.
My brain feels crazy.
So, yeah, 4 is we have one set of 4s, no 2s, and no 1s.
Oh, okay.
5, we have one set of 4s, no 2s, and one set of 1s. Okay? Now go over here to all the way up to 29. Okay? We got one set of 16s, one set of 8s, one set of 4s, no 2s, and 1 set of 1s.
Slay. I get it. Wow.
Okay? Yes?
What is 32 in the binary system? 100,000?
You can't say it that way. It's not 100,000.
Because that doesn't count as the
I know what you
1, 0, 0, 0, 0, 0.
Okay. Well, I mean,
Okay, so let's compare decimal, hex, and binary. So the digits 1, 0 again. Okay, if it's decimal, that's 1 set of 10s and no 1s. 10. In hexadecimal, it's 1 set of 16s and no 1s. So 1, 0, that means 16 in hex. But if it's binary, that's 2. 1 set of 2s and no 1s. Does that make sense so far? Everybody with me on that?
So are we sure that it's still 10?
Well, it depends,
That's where
right?
So a 1 is a set of 2? That's it.
Yep. So in binary, each little slot is 2 times greater than the one before it. So you start with 1s, and you can either have no 1s or you can have 1, 1. That's it. There's no option for 2 1s. Okay, because you just don't have a digit to represent that. So you want to go to 2, you got to plop over here. So you got 2s now. 4s, 8s, 16s, 32s, and it could go on forever. 64s, 128s. Are any of those numbers sounding at all familiar to you? Like,
Well, there's like 16-bit or bit audio.
yeah.
8-bit audio. The 255 is the max of MIDI because 0 counts as a digit.
Yep.
Counts as a value.
Yeah. So when we say things like 16-bit audio, what we mean is we're encoding the audio using 16 bits. What would be the places there? So this is 1, 2, 3, 4, 5, 6 of them. So the 7th would be 64, 128, 256, 512, 1024. Are these numbers that sounding familiar?
It's that game.
at the game, yeah, 2048.
Flag game.
1024, what would be the next one?
2048, the game.
Yep. 2048.
4096.
Yeah. So you know, if you had, as long as you had enough little bits, enough little switches that you could use to be 1 and 0, you could encode any number. It's just not really efficient, right? It's but the computer doesn't care because it doesn't know any different. The computer has no agenda, right? It just it's just a bunch of switches. And it's just going to turn things on and off. It's like, whatever, this is normal to me. Okay? Weird to us, but normal to the computer. Totally normal. Okay? And it can turn those switches on and off really, really fast. So let me see if I can get my my remote going here. Let's see. And then I can write.
What device is T-Mobile?
I don't know. Oh, that's my phone. It's Timon, like the Shakespeare play, Timon of Athens. It should work.
Shakespeare pronounced that.
That should work. I don't know why it's not. I wonder if I need to put it on the other network. It won't let me do that. might need to. Well, okay, that's not connected. Let's do this the old school way, shall we? Since I can't get this to work. So we'll go over here. We'll use some non-digital technology. If you all knew how expensive these markers were. All right. So let's do some counting. So if I wanted to do the value of 127 in binary, how would I do that? 127. Well, let's just draw out the slots first, okay? So you've got ones, you've got twos, you've got fours, eights, 16, 32, 64, that should be enough. Okay, so if we want to do 127, okay, well, we certainly want 64, right? So, we're 64 into it. Is there room for a 32? 127. So what's 64 and 32?
Be 96.
Okay.
Right?
So is there room for 16?
96 plus 16. I should be able to do that a lot better.
Where does that get us? 112. Okay. So is there room for an 8?
Yeah.
There is, yeah.
That gets us to 120, right? Okay. So is there room for a 4? Okay. Now we're at 124.
Yeah. We get a 2 and a 1. Oh, it's 227.
Now we get to 126. 127. See how that works? Okay. Now.
I want to take some Windex to that.
We have cleaner somewhere. That's a hexadecimal number. What is that in binary? You want to know the trick?
Yeah, I was like, I don't know. I feel like it would be a bad idea to go the other way, to go to decimal.
Okay. What's that in binary? 1111, which is that's an 8. 4, 2. Yeah. 2 and 1. Right? What is that in binary? Well, there's no 8s, right? So that'll be a 4 and a 2 and a 1. So what is 7F in binary? And what is that in decimal? What is that in decimal? We just did it. 127, right?
Zero threw me. I was like, where did that zero come from?
So, computers think in chunks of 8 like this. We call that a byte. A byte is 8 bits. And computers think in chunks of 8 bits. They call them bytes. Okay? Now, what would be a kilobyte? 1,000 bytes. So 1,000 of those is a kilobyte. What would be a megabyte? Yeah. A megabyte is 1,000 kilobytes. Okay? A gigabyte is 1,000 megabytes. Okay? So it's all about the number of bytes. All these things these numbers you've thrown around all your life with computers are like, oh, that's a 1 gig file, or that file is 2 megabytes. What you're talking about is how many of those chunks of 8 does it take to encode all of this information? Eric?
Are each of those chunks of 8, but one of them is called a nibble?
Well, this is computer science humor, you see. So, so if 8 bits make a byte, 4 bits make a nibble. And so it turns out that an 8-bit number can be represented in hex using only 2 digits. Okay? So if you did 1, 1, 1, 1, 1, 1, 1, 1 in binary, what would that be in hex? What's 1, 1, 1, 1 in hex? Well, we know already did that, right? It's F. So it's FF, which turns out to be 200, what?
Somewhere in here you lost me. I'm going to be so honest.
Okay, let's do it. So this is 16. This is 32. This is 60, 64, and this is 128. Okay? So, what is 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1?
255.
255. So that's 255 in hexadecimal. That is 255 in decimal. Which means a byte, the largest value that a byte can encode is 255. But here's an interesting little side note. Even though a byte, which uses 8 bits, the highest value that it can encode is 255, there are 256 possible combinations. What's the extra one? What's the byte that is the 256th combination? All zeros, right? So 1 byte can actually have 256 possible combinations, but it can only contribute a value of 255 at the most, unless you decide that 0 counts as something. So let's say, for example, you're writing a MIDI protocol to allow you to use bytes to remotely control other things, and you want to have one more option. Well, you could tell the thing on the other end that 0 is a thing. When you get 0, do this. So even though 0 doesn't count as a value, it does count as a combination of bits, and therefore could be activated as a thing that has happened, right? So now you get 256 possible things that you can do, as opposed to only 255, and that's one more, and it didn't cost you any money, and you didn't have to like add any more hardware, right? So sometimes this will happen, is you start counting 0-based, where 0 means something. Okay, Seth?
Is this why
Oh, look at that! You made a connection. This is why. This is why IP version 4 addresses are 4 numbers, and each number can range from 0 to 255. Why? Because each number is encoded in a byte. And you've been wondering all this time, why can't I make it 256? Now you know why. These are the things I think about.
Like, I
But
figured that's the reason. I just didn't. I just put it on college shit. I just was like, okay, gotcha.
Okay. So that's the kind of stuff that explains why we need to understand this, right? Why it matters. Why understanding the relationship between binary and hexadecimal and decimal is important, because all the tools we use are thinking in binary. They're thinking in bytes, these combinations of 8 bits. So everything happens in 8 bits, which is why digital mixing consoles, which are just big computers, do fader banks in groups of 8. and allocates buses in factors of 8. Right? And there's just all these things. It shows up everywhere. Why 8 is this magic number on a computer? It's because of 8 bits in a byte. Computers love the number 8. Okay? Okay, everybody all right? Everybody with me? Okay. How are we doing on time? So good. So, seriously, have I lost anyone? We can talk about this a little bit longer if we need to.
I don't think so, but also I'm not 100% sure.
Yeah, it's like, if you asked me to start, like,
If you set me free for a while to try to mess with it, then I can find out if I.
Okay. Well, what I want to do now is I want to show you how you can use this information to make sound. Okay? Does that sound interesting? Let's do that. Okay. So, so let's say we want to teach a computer to do sound. This is. So here's what happens. So we know about the air thing. Okay, we've learned about that before. Okay, where you make sound because you squish air together and stretch it apart. Squish it together, stretch it apart. You do that fast enough, it starts to move your ears, and that is sound. Okay, and we know that you can use a microphone to capture that change of air pressure amplitude and encode it into an electrical signal, which is what's happening here. So that's electricity. And we can graph that as a voltage wave. Okay, we know about that. And we also know that you could then convert it back into sound by sending that voltage wave, albeit a much higher voltage, into a loudspeaker, and that loudspeaker will push and pull the air again and turn that back into sound. Okay? Well, what if you wanted a computer to be able to do sound? Well, remember, a computer is binary. Counts in binary. It does not do curvy values. Okay? It just doesn't do it. So what you end up doing is you have this little thing called an analog to digital converter. So when we say digital, what we mean is binary. When we say digital, we mean we're doing this in binary with a computer. So what an analog to digital converter does is it looks at this voltage that is coming in, that's fluctuating, okay? And at some determined interval that we decide, it does something called sampling it. So it samples that voltage. It says, what is the voltage? Every time you see this thing drop, it's saying, what's the voltage? 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 Every time it asks that question, it stores that value in a digital number, a combination of zeros and ones, and just makes a whole list of them. It makes a list of those numbers. Every time it punches it, it's like that's another number, another combination of digits, another combination of bits, another combination. It just makes a big list of them, okay? And it can use that now to recreate that electrical wave again. So it could then, you could get a digital to analog converter that would feed those numbers into it, and it would say, oh, that represents this voltage, and that represents this voltage, and that represents this voltage. Okay? Now, it gets a little weird, though, because, let me see if I can show this to you. Yeah, okay. So here is a graph of a wave, right? This would be the analog voltage wave, okay? And at intervals, we are sampling it. We are sampling the value and we're saying it's that much, it's that much, it's that much, it's that much, it's that much. And we're storing that in a digital number. Well, when we feed that back into the digital to analog converter to turn it back into electricity, this is what it's going to do. I don't have that turned on, do I? Because of the limitations of the way that the computers count, there's only so many possible numbers, right? In a byte, how many possible combinations of those bits are there? 256 possible combinations, which means if you are using 8-bit samples, you only have 256 possible voltage levels that you can encode. And so if your sample, or if the actual voltage falls in between one of those 256 values that you're able to use, then what's it going to do? The computer can't count that value. So it's going to just use whatever the nearest value is. And that's what happened, is you saw this shift. So here we've got 8 possible values that we can encode. And if we go back here, step back. So there's the actual values. Now watch what happens when I impose that 8. See how it shifts? It shifts them down to fit into one of those 8 values. So this one that used to be here, it's like, okay, well, that's going to have to be this instead. And this one that used to be here, that's going to have to be this. That one it can do. That one went down. You see what's going on? This is called quantization. Yes?
So this is measuring the amplitude signal, basically?
Yeah.
Are you saying that like when it digitizes sound, that it also compresses sound? Or is it just that like...
Not necessarily. I'm going to show you that in a second here. But what it does is, because this is registering amplitude, okay, the number of bits that you're using to encode these values determines the possible dynamic range you have. Okay? So the loudest thing is a fixed thing. That's all the bits turned on. Right? All the bits set to 1 is the loudest number, and that's a fixed thing. The only question is, how much lower than that can you go? And that depends on how many bits you have to work with. Okay? If you only have, in this case, 4 bits, then, well, no, it would be 2 bits. This is 2 bits. Then you could do 8 possible values. 8 possible combinations in 2 bits. Because you could do 0, 0, you could do 0, 1, you could do 1, 0, or you can do 1, 1. Yeah. So we can do, you're right. So we go 0, 0, 0, 1, 1, 0, 1, 1. We can do 0, or 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Yeah, there's our 8. Okay, so it's actually, it would be 3 bits. 3 bits to do 8 values. So these are 3-bit samples. Okay? 3-bit samples gives us 8 possible combinations, and we've got 8 lines here to represent the different values. Okay? It's not a lot of options. Because then what happens is this gets encoded. So let's step forward here and see what we're talking about. Okay. So what this is trying to show you is this concept of aliasing, which is that in order to reconstruct this later back into the wave, the source wave, you have to be sampling it sufficiently. If you don't have enough samples, then ultimately the computer just feeds that list of values into the converter, and the converter just plays connect the dots, and it draws the wave. In this case, we didn't sample it. We didn't have enough samples. And therefore, the wave that comes out when we go from digital to analog is a lower frequency. Okay? So there's 2 things you have to care about. You have to care about the number of bits you're using to encode these samples. That determines your dynamic range, the difference in loudness that you can encode. But the number of samples you're using, or the rate at which you're sampling them, how many samples every second, we call that the sampling rate, that determines what frequencies you can encode. Okay, so lower sampling rates mean you are limiting your range to lower frequencies. So you want higher sampling rates. You want to encode higher frequencies, you need higher sampling rates. This is an example of where we had not enough samples. Our sampling rate was too low, and so the wave that comes back out is a much lower frequency. Okay? So ultimately, the rule of thumb here, I don't know if I have this or not. Oh yeah, here we go. Okay, so the rule of thumb here is called the Nyquist theorem, which basically says that your sampling rate needs to be twice as much as the frequency you want to encode. Okay, so if you want to encode 600 hertz, then you need a sampling rate of at least 1200. And it can do that. Okay. But what if we go to 2000? This ends up being how it samples, but it can do it. Okay? That's enough samples to recreate the 600 hertz. But if we only do 500 hertz sampling rate, so the black is the starting frequency. The red is the frequency that results, because we didn't have enough samples. Okay? Now here's the good news. Aliasing is not, in actual practice, aliasing is not something you have to worry about. Because what happens is the converters that do the analog to digital converting always have an EQ filter, filtering that audio before it goes through the converter. And it's a low-pass filter. And it filters out all the frequencies that cannot be encoded with the sampling rate you're using. Okay? So it never allows you to encode a frequency that you cannot capture given your sampling rate. So if you have a sampling rate of 40,000, for example, then the filtering is going to be set up in such a way that you will not be able to encode a frequency more than 20 kilohertz, because that would alias and you'd end up with weird things. Okay? But the rule of thumb is you need sampling rates that are twice as high as the frequency you're trying to encode. Now, generally speaking, the range of human hearing is thought to be around 20 hertz to 20,000 hertz. So to encode the range of human hearing, you need at least 40,000 hertz, 40,000 samples per second. You need to be taking that snapshot 40,000 times every second in order to encode all the frequencies that the human beings can hear. What's the lowest sampling rate you've ever seen or been able to dial in on a piece of equipment? 44,100 is probably the lowest you've ever seen. Which means you could encode, the highest frequency you could encode is 22,050, right? Because that's half of 44,100. So that's, 20,000 hertz is the highest frequency thought to be on average that humans can hear, but that's an average. Some people can maybe hear higher than that. But also the filters are not perfect. There's no low-pass filter that is a perfect brick wall. It's going to, there's a slope to it, okay? So you usually want to be at least 44,100 hertz sampling rate to be able to encode some of those extra frequencies that are just going to get through a little bit quieter because of the imperfections of the filter. Now, 44,100 is the standard sampling rate for consumer digital audio. Listening to things on your phone and stuff like that. Professional sampling rate standard is 48,000. So like when you work on like a film, for example, it's going to be 48 kilohertz sampling rate. Or any sort of professional work, most professional mixing consoles will hopefully default to 48,000, or at least that will be one of the options. It'll give you 44.1 or 48, depending on, you can choose, but either will work because they're both, capable of encoding the range of human hearing. Okay, but the filtering takes care of the aliasing so that you don't have to worry about it. Now let's take a look at what this bit depth thing does, because this is where it gets a little interesting. So here I have a sine wave. Okay. And right now, I am encoding it with 16 bits. So every sample, the sampling rate is whatever the sampling rate is of the audio interface, which is 44,100. Okay? And so every one of those samples, 44,100 of them a second, are encoded using 16-bit numbers, because that's my bit depth right now. But what happens if I lower the bit depth? Well, it's going to have to start quantizing. So what if I go to 8 bits? Well, you probably don't hear much of a difference yet, but there's an important thing that has happened. Our potential signal-to-noise ratio, which is the range of loudness that we can encode before we hit the noise floor, is only 48 dB right now, which means the loudest thing is the loudest thing. And that means the quietest thing that we're going to be able to encode can only be 48 dB quieter than that before it dips below the self-noise of the system. Okay? Whereas when we were at 16 bits, our potential range was 96 dB. So when you got 16 bits, the quietest sound that you can encode digitally is 96.3 dB quieter than the loudest thing. That's a pretty big range. That should be sufficient for really anything that you do. Okay? When you go down to 8, though, you only get 48 dB of potential range. And, that's okay for now, but what happens if I start getting lower? Now I'm at 4 bits. Now my range is only 24 dB. And you're now hearing something, aren't you? What you're hearing is the quantization error. Because you can start to see it here. Let me go down to like 2 bits. Okay, the red wave is the digital wave. And it's building it as though it's like a step. Okay? And so there's a lot of values that are getting like quantized into something different. And it has to do something with that extra energy, and that turns into noise. It's called quantization error. And that is the results in high frequency harmonics and noise gets generated as a result of that. That's why the noise ratio, signal-to-noise ratio goes down. So we have a 12 dB signal-to-noise ratio now, which means the quietest thing we can encode can only be 12 dB quieter than the loudest thing. Well, with a sine wave, there's potentially more, a wider range than that. Okay? And so we're getting errors. This is the noise. That's the noise that's left over. That's called the quantization noise. It's the result of not having enough bits to encode all the possible values you need. But if I go up back up to 16 bits, I don't have any noise, because I got enough bits to encode all the values. And you can't even see the steps anymore. Like if I try to slow this thing down, oh, I can't get that. Oh, there we go. I can't see it. So you can't really see the red line anymore because it's encoding it pretty well. But when I start stepping down in bits, you start to be able to see that I've got limits in my discrete values in each sample. Okay? And that has an impact on this signal-to-noise ratio. Now, I said that 16 bits gives you potential of 96 dB of potential range, and that should be plenty. I mean, you've probably never in your life been in a room where there could be a range of 96 dB between the loudest thing that you could tolerate and the quietest thing you could hear, because you've always been in rooms that have higher noise floor than that. I mean, this room has a noise floor, right? I mean, you can hear it. Okay? So 16 bits ought to be plenty, as long as your incoming amplitude is enough. Because look what happens now if I reduce the amplitude of my wave going into the system. So if I take it down pretty low, look at that. I'm still at 16 bits. And even though my potential signal-to-noise ratio is 96 dB, my actual signal-to-noise ratio is only 81 dB, because there's a bunch of those bits that I don't get to use to encode values in. Okay? There's some leading zeros there that I don't get to use because my peaks are lower. So that range of bits, those chunks of, it's 2 bytes in a 16-bit sample. It's 2 bytes, a total of 16 bits, 16 zeros and ones. I'm taking some of them out of the picture because I just don't have a signal high enough to use that value on. And therefore, if I look at the difference between the peak value and the quiet value, it's less. I've lost 10 dB of potential signal. Not because I'm not using a sufficient bit depth, but because I've got bad gain structure. I'm not feeding that analog signal into the converter at a high enough amplitude in order to get that full 96, which means we start to run into real trouble sooner when we start reducing the bit depth. So if I put on the quantized signal and I start going down, like if I really duck this amplitude, and then I put it up over here, I'm at 7 bits, and you're starting to hear the distortion and the noise. Right? Whereas before I had to get all the way down to like 2 bits. So this relationship between your signal amplitude and your bit depth is super important. Because you are limited to these 8-bit chunks. You can do an 8-bit sample. You can do a 16-bit sample. What would be the next highest value you could do in a sample? 24, because you could do 3 bytes, right? So you could do 8-bit samples, you could do 16-bit samples, you can do 24-bit samples, you could do 32-bit samples, right? The more bits you use, the more possible values you can encode, and the bigger that signal-to-noise ratio is. Now, 16 bits ought to be plenty. I mean, a range of 96 dB ought to be plenty, unless you're getting lazy with your gain structure. And if you're sending signals in that are too quiet, then you are not using that full 96 dB potential. Even though you have theoretically 96 dB of range, you're only using a third of it because you're feeding the signal too quiet. You haven't turned up your preamp, you haven't done whatever, you recorded it bad or whatever, and it's going in too quiet. And now you effectively have a 4-bit sample because you're leaving a bunch of those bits unused. Okay? But what if you went ahead and went to 24-bit samples? Even though 16 ought to be plenty, right? 96 dB ought to be plenty. Well, if you went to 24-bit, now you got a much wider range of values, don't you? Which means you can be a little lazier. That's really all the 24-bit gets you, is the ability to be a little lazy. Let me demonstrate. So I have, oh, here we go. So I have a bunch of different values here, or different samples here. This is just me playing the piano, okay? And I recorded myself at different sampling or different bit depths, okay, and different input levels, okay. So this is the 16-bit value recording with really high amplitude. Okay, so the mic and the preamp are really hot. Okay, and I put it in as 16 bits. Okay. Now here is a 24-bit of same scenario, same amplitude, same everything. I don't know about you, that sounds exactly the same to me. Okay, and it should, because really, I was doing a really good job with my preamplifier, my mic position, and all that kind of stuff. I had really hot signal going in, and the 16 bits was plenty. Okay, well, what if I got a little lazy? Okay, here's the 16-bit sample, but really low amplitude going into the converter. Okay, I've got to turn up the output so you can even hear it. Let me play that again. Okay, now here's the 24-bit version of that low. Still sounds about the same, right? Well, here's where it gets interesting. What if I compressed it? So what if I start messing with this? We never do that, right? We never record something and then mess around with it. Okay, well, let's see. I'm going to take my, this is the 16-bit high input level, but I'm going to compress the dynamic range a little bit, okay, with some makeup gain. Okay, here we go. Okay, no big deal. Well, what about the low one, if I compress the low amplitude one? You should be able to hear a difference there. What do you hear? There's some noise. So there's some noise in there compared to this one. This one's a lot cleaner. There's no hiss in it, right? So I'm already starting to hear that some of that noise, some of that quantization noise. Okay.
Is that your scratching my
scratching?
Like when do on that part of your like a
That's the pedal. It's a Steinway piano. They make the pedals make that sound. Yeah, that's the pedal. Okay. Well, what if I compress it and then I normalize it? Normalizing, I push it all the way to the full range. Okay. Well, this is the high range, so this is me recording it well, and I compress it and I normalize it. Okay, no big deal. Sounds fine. Well, what about this one? So now I take the one that I recorded at too low of a level, which means I'm getting a lot of quantization error. I'm not using all the bits. Even though it's a 16-bit sample, I'm not using them all, and so I get problems. So here's now I start manipulating it. Now let's see what we get. Now listen to the tail of this. Okay, what's happening? It's fading out, right? And as it's fading out, the value's getting lower and lower, and we're running into the limits of our quantization values, right? The limits of those bits. We're running out of values we can encode, and so it's bumping them all over the place. And we get all that noise because it just doesn't have the resolution to encode that fade out. Okay? Well, let's look at the 24-bit version of this. So 24-bit version, compressed with good input level. This is what it sounds like. Pretty good, pretty clean, no big whoop, right? Here it is, normalized. Listen to the tail. Okay, pretty good. Now let's compare that to the 16-bit one. Okay, it's pretty close, right? There's just a little bit of noise, tiniest little bit of noise in that 16-bit one, but not enough that I would care about, right? So either way, that one's fine. But let's look at the low one now. The low one that was so bad in the 16-bit. Let's listen to this in the 24-bit now. They still have some noise, but let's listen to the tail now. Okay, it's able to do the whole fade out, as opposed to this one. Okay, so the 24-bit just had a lot of extra bits in that value to encode that smaller range. And so it could, even though I was a little lazy in my gain structure when I recorded it, I still had enough bits to encode that fade out, whereas I didn't with the 16-bit. The 16-bit really should be plenty. If you do everything right, 16 bits is more than enough. The only reason people use the 24 bits is so that they don't have to care as much about all that gain structure stuff. So you're thinking, great, why don't we just do 24-bit all the time? That sounds a lot easier. Then I don't have to worry about all this stuff. Why would that matter? Why would we not just do 24-bit all the time? Makes the file bigger, right? Remember, with 24-bit samples, we need 3 of these chunks. Whereas with a 16-bit sample, we only need 2 of them. So that 24-bit file is going to be 50% bigger on your hard drive. It's going to take up 50% more space on your computer than the 16-bit one do, because you got to encode all those bits, whether you use them or not. You'll You're probably not using all of them, but you got to have them in order to have the number. And so the 24-bit samples are just bigger. And maybe you've got all the space in the world on your hard drive and you don't have to care about that, fine. But maybe you don't. Maybe that 50% is a lot to you, and maybe you need that space on your drive. And you can save yourself a lot of space on that drive if you can get smart about your gain structure and make that 16 bits go as far for you as it is capable of going. How are we doing? Questions so far?
So, say you want to save storage, then you record at 16-bit. You want, I guess, when you record it initially, you want a signal to be as hot as you can. Is that just through gain, or just like also just placing the mic?
It's both, yeah. I mean, you want to get so that when that signal gets converted to voltage and hits that digital to analog to digital converter, you want to be hitting that converter with whatever the loudest thing is, should be the thing that lights up all the bits. That's ideally what you want. But there's a danger to that, though. There's a real danger to that strategy. Anybody think what it is? Clipping. What would happen if you guess wrong and that voltage that's coming in is higher than the biggest value that can be encoded with that 16-bit sample? What happens?
You can't encode it, right?
It quantizes it, right? Just like it was doing here with the low signals, it does that now with a loud signal. And you get, so listen, I've got some examples of that here. Here is the 16-bit version, but I overshot. I clipped the converter. Okay? Here's the 24-bit version, same mistake. So whether you're doing 24 bits or 16 bits, if you clip it, it's clipped, right?
Maybe a hair better, but not really.
Clipping is clipping, right? If you clip it, you're done. You can't undo that.
So the sound, that sound of clipping, is that just the highest sound you note for? Is that like what it is?
It's the same thing that's happening here. So just like when I go down to these lower bit depths and it's quantizing it and we get the step ladder, same thing happens when you clip it. You get that same flat peak. Okay? So it's not that you ran out of bits so much as you just exceeded the bits. Whatever the highest value that you could do was just, you went out. Now, in actuality, the highest value is an electrical thing. Okay? The highest value is all the bits turned on, regardless of how many bits you're using. And the only question is how much quieter than that can you go. But there is a maximum input voltage for that converter. Okay? And whether you're using 16 bits or 24 bits or 32-bit floating point, there's a maximum voltage that you can feed into that, and it will clip it. And if you clip it, you're dead. It doesn't matter what you do. You can't undo that. There are some plugins that attempt to declip things, but yeah, they don't. Anybody ever had those work really well for you? Not me. I mean, they're okay, but I'd much rather just have not clipped it in the first place. So this is the danger, and this is why you see a lot of people going ahead and saying, it's worth the extra 50% on the file size for the 24 bits because I don't have to be riding the edge of clipping when I'm recording. Because even though 16 bits ought to be plenty, it's only plenty if you're using all the bits. And you're only using all the bits if you're sampling it right below the clip point. And who wants to do that? Well, if you're paying attention, you got the time to really get that right, then yeah, sure. But a lot of people don't. A lot of people think, well, I don't know. the musician might come in, for example, and they might play louder than I just did. And then it's going to clip, and then I'm in big trouble. That's happened to me. I've done recordings where, like, I thought I had it all lined up, and then suddenly they bring something way bigger than I ever thought they would. And suddenly we're at the end of the song, and it was the perfect take, and I clipped. And it was like, I'm so sorry, that was perfect, but we have to do it again because of me. Okay. So this is where you could start to make the argument for the 24-bit samples. It's like, well, I could leave those extra 8 bits of the sampling of the sample as my headroom. So I don't have to ride the edge of the clip point. I could leave those extra 8 bits as headroom, and then then I still have the 16 left, which is plenty, right, to do what I need to do. And I can manipulate it, or I can mess with it, I can compress it, I can work with it, and I'm just leaving those extra 8 bits as headroom. I'm not really using them. It's only if, things get louder than I think they will, right? Or I just have a trickier fade out or something like that, but you're going to leave those as headroom, okay? And so for some people, that's worth it, to not have that risk. Does that make sense so far? So hopefully these terms sampling rate and bit depth are starting to mean something to you now. And maybe they didn't before. You've probably encountered those terms before. In doing sound, you've encountered things like sampling rate, 44.1 kilohertz, 48 kilohertz, 96 kilohertz, 190. Well, we'll get into that in a minute here. But and you've probably encountered things like, well, 16-bit, 24-bit, 32-bit samples. Like, hopefully that's meaning something to you now. You're understanding why those numbers are what they are. Those bit depths are in chunks of 8 because of the way that binary counting works on computers. They must do it in chunks of 8. That's just how they work. Okay? Now here's a little secret that not very many people talk about. Inside of the computer, like when you're working in Logic or Pro Tools or whatever on your computer, it is running all of that math inside. When you're running like a plugin, or you adjust some level, or you mix something together, and it's running math, it's doing that using, these days, 64-bit samples.
Right, yeah.
Because that's what the CPU does. Really, it's like, yeah, well, it's depending on what kind of CPU you have, it's either 32-bit, called floating point, or 64 bits, which means like there's your potential to introduce quantization noise while you're messing around inside of the application is really minimal, because all of that processing is done much higher bit depths. The bit depth part where you have to start caring about it is when it comes in and when it goes out. Because when it goes out, then it goes through the bottleneck of the converter, which is the little box that converts it back into analog and lets you play it through your sound system. Okay, that's when you start having to care, because those aren't necessarily going to be running at those higher bit depths. Okay. So once you get it in, as long as it's clean when it comes in, when you're messing with it inside of the computer, your potential for disaster is really minimal, right? But you got to get it in clean to begin with. So you got to make that choice. It's a choice you got to make when you start. When we're going to do a recording assignment in this class, and you're going to have to decide, am I going to go 16-bit or am I going to go 24-bit? Depends. What do you want to do? These days, it doesn't really matter from the computer's point of view, because the computers are fast enough that they can run that 24-bit just as fast as the 16-bit. We used to have to care about that. Don't have to care about it so much more, but maybe you care about that extra 50% of storage space. Maybe your drive is not got a lot of space left on it, and maybe running a 24-bit is going to like fill you up, and you don't want to do that. Then you can make an argument for 16-bit, and you just have to pay attention to your gain structure a little bit better. Okay. Everybody feeling okay? that's probably where we'll stop. I think I've hit your limit. Okay. So next week, we've already gotten a little ahead, isn't that great? So next week, what we're going to do is we're going to look at how does the computer actually work? What does it really do? You understand now how it does math and how it can do sound math. Okay, that's what we've talked about today. Is you now know about binary, you know that hexadecimal can abstract binary in a way that we can do it in our head, and you now know that how you can use binary numbers to encode sound. Okay, so now on next week we're going to look at what is actually happening in the computer. What is it doing when it's okay? All right. Questions anybody has? You can ask. I will explain.
Can you explain the distortion again? Like the relationship between the distortion?
Yeah. Okay. So you see how here this nice curvy wave that we started with has turned into a jagged wave? That's just because we're so low in our bits, right? We only have a certain number of values, and so it's getting quantized. So we can't make that smooth wave. We can only make this stepped wave. Okay? Well, when you get these big steps like that, that creates harmonics. Okay?
Oh, yeah.
So when that gets converted back into analog, you've got all these are all the harmonic frequencies that got generated by that square wave. Okay? When you feed that through.
Is that kind of the same with like flip-flop? Was it a flip-flop?
That's exactly
Yeah.
what I was
Yeah.
thinking.
So when it distorts, it creates a harmonic
Same thing.
frequency.
Same thing, right? Well, so that can happen because you don't have enough bits to encode the amplitude, right? You haven't necessarily clipped anything. You just quantized it because you don't have enough bits. I'm only working with 3 bits here. And so it just can't, there's only a certain number of values it can encode. And so it just quantizes them and you get these little square wavy things, okay? Well, the same thing happens when you clip. So I could have plenty of bits to encode that value, but if I exceed the top of this screen, for example, if this screen represents the limit of what I can do, if my sample goes all the way up here, what's going to happen? Well, all it can do is turn all the bits on to 1, right?
Yeah.
That's all it can do. And all the bits to 1 is the top there. And if your signal is bigger than that, then it's just going to cut it off and you get the same thing. It's just chopped off again. And you get all those harmonics again.
So the sound is from the encoder, right?
What's that?
The sound is coming from the encoder?
Like that's the
Like the
digital
harmonic,
noise
like,
that's
yeah,
happening?
the reaction.
It comes after that. So it comes when you feed it back through the decoder. So now it goes from digital back to analog.
And then when it comes to
And when it comes back into analog, you get all those extra harmonics, right?
Is that because it's analog, then you can have those resistors that filter out certain harmonics and that kind of stuff? If we're talking physical?
Well, you could, right? That's one way of dealing with it. It doesn't completely solve it, though.
Right, but it
Right.
at least helps filter
But it
out
could.
more too.
It could, yeah. Yeah. So the way that this kind of manifests, have you ever like worked in Logic or Pro Tools or something, and you have seen like one of your channels clip, but you don't hear the distortion?
yeah,
Why? Because you can't actually clip internally because it's working with these enormous values, right? It's working with 32-bit, 64-bit values. So so that clip indicates a clip that would happen if you ran that through your converter right now. Okay? So you don't hear the clip, but you see it happen. And seeing it happen just means, hey, you've exceeded the limit of your converter when you play this back out later.
So that's when you would know.
That's when you would start to hear it. And you could have it clipping on like a channel here, but as long as the main output isn't clipping, then you're not feeding a signal through your converter that goes into your headphones that would give you that distortion, right?
So a channel can clip.
Yeah.
And you won't, none of that, you won't hear any of
Yeah.
that. Okay.
Oh, so like if I'm having like a drum, right, put it in a bus and it's clipping in the bus, it won't.
Right.
That's why when I've been doing stuff, I'm like, it's clipping in troubles, but it's
Yeah, but you
not.
can't hear it.
Yeah.
That's why. Because that clip light just means you've exceeded the limit of what your converter is going to be able to do, but the computer inside can deal with it. It can make a bigger number because it's got 64 bits to work with. Okay? It's just giving you a clue. It's saying, hey, you've lit up all the bits of the 16 that are on your converter. I'm okay, but the converter's not going to be if you feed that through it like this. So that's why that's happening. But but the only way you can understand it is understanding the concept that, oh, it's 8-bit chunks, and you can only have so many of them, and different stages of your signal flow are working with different sets of those chunks of 8, right? Your converter is not working with the same number of bits as your CPU is. And so the CPU is like, yeah, fine, whatever, I'll make that drum as loud as you want. But the converter is going, if you send it this way, I don't have that many bits to work with, and that's going to distort, and you're going to hear it. Now, if you clip coming in, you're done. It's distorted forever. Okay? Whatever that distortion is will be there forever, no matter what you do internally, and no matter so that's the thing you want to definitely avoid. You do not want to clip when you're doing the analog to digital conversion. Ever. There is never a scenario where that is okay. Like, never let that happen. Yes.
So could you then just record a 24-bit, and then when you export it, just say, yeah, now I don't need that extra headroom.
Yeah. I do that all the time.
16, please.
I do that all the time.
Okay.
Yep.
Because, yeah, maybe I want the extra headroom, but once I've done it.
Yeah, once you got it all mixed, you got everything laid out, and you got your range, your dynamic range, everything's all like we like it. Yeah, maybe you don't need those extra 8 bits. Great, dump them. It only becomes a problem in that conversion. Only becomes a problem when you get to like the really low level, like on fade out tails and stuff. Sometimes you might run into trouble. QLab used to have that problem back in the day. QLab would like get grainy on fade outs. And it was because of that, because it was just running out of bits. But the way we do that is it uses what's called dither. And dither, interestingly enough, is just noise. And so what's happening is a dither is a little bit of digital noise that you introduce. And it only really comes in, you can't really hear it, but it only comes into play at the end of those really low, like fade outs and reverb tails and stuff like that, when you're kind of running out of bits. And the quantization is like dumping too many things to 0. Okay? And what the dither noise does is it introduces this little bit of noise that forces it to alternate between 0 and 1, 0 and 1, 0 and 1. And then when you feed that through your digital analog converter, it creates an average. And you don't hear that weird that's happening. That's what dither is. So when you're going from 24-bit to 16-bit, for example, there is the potential that you lose the tail because you've given up 8 bits, right? And so if you do that and you're starting to hear that, one of the ways to overcome that is to introduce a dither noise into it, and then it will introduces that random noise into that tail, and so that tail that is going, it's now introducing noise like this that goes, and when you feed that through the converter smooths that out. It's a little trick. But that's the only time you really have to care about going down from like 24 to 16, for example. Because you're giving up 8 bits, and theoretically that's 20 dB or something you're maybe giving up. Probably fine if you're doing okay, but maybe, I don't know, you might. So there you go. Other questions? Yes.
Unrelated. So the bits, if we'll use the 3-bit because that means 8 levels that it can sample, are they split between positive and negative voltages then?
Yeah, basically.
Okay, it's not like, you have 8 above and 8 below. It's, you kind of have 4 and 3 10.
That's my understanding.
Okay. Because that's kind of what it looks like there.
Yeah.
Is that there are 8 total steps. Some of them happen to be negative.
Yeah.
So presumably 0 voltage would be the middle.
Yeah, I don't think I will admit I don't fully understand this,
Yeah.
but I don't think the computer thinks of it that way.
No.
But like I don't think the computer thinks about it as like positive, negative. The computer just thinks about it as
The computer thing just moves everything up
yeah,
half of the way for
Yeah.
it. So, oh yeah, that's fine.
yeah,
Then it doesn't need a positive minus.
yeah. It's an offset thing that it does.
Sure.
I'm pretty sure that's how it works.
But essentially, yeah.
But
you-
effectively, yes.
You have half the amplitude on the
Yeah.
other side.
Yep.
Whatever those numbers actually are, I don't know.
Yeah, there's somewhere in my book we wrote about that. I don't remember. As far as like how you calculate that,
Yeah.
how you get 96 dB out of 16 bits.
Sure.
Like there's actual math so you can figure that out. But that is not information I have to use every day, and so it has been filed away somewhere way back there, and I can't possibly recall it in a moment's notice. Yes.
Maybe you said it and I missed it.
Yes.
But I know you said that dithering is good for like if you're going from 24 to 16. But is it something you hear at all if you play it at 24?
Nope. It's like it is noise that is just like it's literally the noise that is bouncing between all zeros and all zeros and 1. Right? It's like way down there. Like in that potential for 96 dB of range, if 0 is the max and negative 96.3 is the lowest, that little dither noise is hopping between negative 95 and negative 96 or something, right? If that. So you don't hear it. There are some that argue because of that internal bit depth that's going on, where the computer, like logic, is actually doing it 32-bit or 64-bit, then even when you're outputting to 24-bit bouncing, you still should put dither on it. And it's a 24-bit dither that's specifically designed to flop between that 0 and 1 on a 24-bit sample, because theoretically you do have the potential for quantization noise because you're giving up bits, right? But at least in practice, I've never encountered noticeable quantization noise when outputting 24-bit, even though we're processing internally at 64 or something, right? I've never noticed that, but I guess there are situations where you might encounter that. I've never found that though. But there are people who swear by that. They say you should put the dither on even if you're dumping to 24. Yeah. But that's all dither is. There's nothing magic. It's just noise. It's just really, really quiet noise that ironically makes it so you have less noise. It's noise that removes noise. Totally counterintuitive, but that's what it does. It works. It's a very elegant little solution to a very weird problem that you see in sound. Okay. Any other questions? Okay. Well, next week, like I say, we'll talk about computers, how they work and what they do, and how they do sound. Okay. What's actually happening? Because the difference between success and failure, when you're trying to get computers to do sound, the difference between success and failure from a technical point of view is all about knowing where the sound is inside the computer at any point in time. Is it in the converter right now? Is it on the hard drive right now? Is it in the RAM right now? Is it in the CPU right now? Where is it? And knowing where it is will help you avoid the kinds of mistakes where you lose work that you've done. Have you ever had that happen where you work on something for a few hours and then like suddenly you do one weird thing and it's gone? That's because you didn't know where it was. You didn't know where it was, and therefore you made the wrong decision about what to do, and you lost it because you didn't know, you tried to catch it in the wrong place. It was sitting in RAM, and you thought it was sitting on the hard drive. But because it was sitting in RAM, it's gone. Right? So we're going to talk about that next week so that you can start to visualize Okay, where is my work right now? Where is it living inside the computer? And knowing where it is most of the battle. Most of the battle of getting this all to work is knowing where the data is at any given point in time. So we're going to learn about that. All right, we're done. Thanks, everyone.